Hello students, today I am going to discuss basic concepts of the subject refrigeration and air conditioning. This particular subject contains various topics like heat engine, heat pump, reversed Carnot cycle, vapor compression and absorption refrigeration systems, air conditioning along with psychrometry. So let's start the class. First of all, what do you understand by refrigeration? So, it is the process of producing lower temperature compared to surroundings. As lower temperatures are to be maintained continuously, a refrigeration system must work on a cycle. So, the meaning of refrigeration is that you have to decrease the temperature of a system compared to the surrounding. System may be a particular room, a place where you want to decrease the temperature. So, dear students, refrigeration system must work on cycle. So, this refrigeration system basically works on air refrigeration cycles, vapor compression cycles, vapor absorption refrigeration cycles. So, there are 2 to 3 cycles on which this refrigeration system works. So, if I will talk about an air refrigeration cycle, then in an air refrigeration cycle, the air is used as a refrigerant. So if I will talk about olden days, then air was widely used in commercial applications because of its availability at free of cost. Since air does not change its phase, that is remains gaseous throughout the cycle, therefore the heat carrying capacity per kilogram of air is very small as compared to vapor absorption systems. So the air cycle refrigeration systems as originally designed and installed are now practically obsolete because of their low coefficient of performance and high power requirements. However, this system continues to be favored for air refrigeration because of low weight and volume of the equipment. So, dear students, now we will discuss what is refrigerant. Refrigerants are substances which are used for producing lower temperatures. So this refrigerant is a medium. It is the medium by the help of which we get refrigeration. So the examples of these refrigerants are ammonia, carbon dioxide, air, water, R11, R12, R134. This R11, R12 and R134 is basically refrigerant name, refrigerant coding. So what is refrigeration effect? Refrigeration effect can be defined as it is the amount of heat that is to be extracted from storage place in order to maintain lower temperature. So refrigeration effect means if you want to decrease the temperature of any system, right? So how much amount of heat you are extracting from that storage place? That is our refrigeration effect. Now students, before discussion of air refrigeration cycles and other topics, we have to understand what is the unit of refrigeration. So unit of refrigeration is basically ton of refrigeration and it is denoted as capital T and capital R, that is TR, and we all know 1 ton is equal to 1000 kilogram. So let us understand that how this ton of refrigeration can be defined. So it is the amount of heat that is to be extracted from 1 ton of water at 0 degrees Celsius in order to convert it into ice at 0 degrees Celsius in 24 hours or in one day. So TR basically represents heat transfer rate and TR is the practical unit of refrigeration. In other words, ton of refrigeration is also defined as the amount of refrigeration effect produced by the uniform melting of 1 ton, that is 1000 kilogram of ice from and at 0 degree Celsius in 24 hours. So we can also understand ton of refrigeration if we are having ice cube of 1 ton. So we have to give heat to that ice cube. We have to give that much heat so that it will convert it into water completely at 0 degree Celsius and in 24 hours. Or vice versa, we can also say if we are having 1000 kilogram of water, then we have to extract that much amount of heat from that 1000 kilogram of water at 0 degree Celsius and in 24 hours that it gets converted into ice. So dear students, latent heat of ice we all know is 335 kilojoule per kilogram. So how we will be able to find out the value of 1 TR, that is 1 ton of refrigeration? So 1000 kilogram into 335 kilojoule in 24 hours. So 1000 into 335, and if we talk about that how much heat we have to extract or supply in 24 hours, so we will divide it by 24 into 60. 24 hours can be converted into minutes by multiplying into 60. So we get the result 232.638 kilojoule per minute. So this value is particular theoretical value, right? But in actual practice, 1 ton of refrigeration is taken as 210 kilojoule per minute or 3.5 kilowatt. So for our calculation purpose, we have to take the value of 1 ton of refrigeration is equal to 3.5 kilowatt or 210 kilojoule per minute. Now we will discuss coefficient of performance of a refrigerator. What do you mean by coefficient of performance of a refrigerator? So the coefficient of performance is nothing but the ratio of heat extracted in the refrigerator to the work done on the refrigerant. It is also known as the theoretical coefficient of performance. So here, dear students, we can see the diagram of refrigerator. This T1 is higher temperature and it is of surrounding, and this T2 is lower temperature, that is of storage, right? So where we want lower temperature, this is that place, this is storage place. So for running a refrigerator, we have to give work input to it. So here we have given WIP, that is work input to refrigerator, and refrigerator is extracting Q2 heat from this lower temperature, from this thermal reservoir, right? So this thermal reservoir is known as sink, this is source. You might have studied it in thermodynamics. So by the help of this work input, this refrigerator is extracting Q2 heat from this thermal reservoir and decreasing the temperature of this storage place. So we are having the formula coefficient of performance of refrigerator is equal to refrigeration effect. What kind of refrigeration effect is being created here? So Q2 is also known as refrigeration effect. We have already seen in last slide. So COP of refrigerator equal to refrigeration effect divided by work input. So Q2 divided by WIP is our COP of refrigerator. If we talk about ideal refrigeration cycle, then ideal refrigeration cycle is basically reversed Carnot cycle, and we are well aware of Carnot cycle, that in Carnot cycle there is two isothermal processes and two adiabatic processes. Isothermal processes are very slow and adiabatic processes are very fast process, right? So we have seen that Carnot cycle is not a practical cycle, but for comparison purpose with other cycles we study Carnot cycle. So here we can see on this TS plane, temperature and entropy plane, that is these two processes are isothermal processes. This process, the downward process, we can see this is heat supply is taking place in isothermal process, right? And in this upper process we can see heat rejection takes place. So we have taken this upper process as T higher temperature, and this lower process as T lower temperature process. So we also know the maximum coefficient of performance for Carnot cycle, for a reversed Carnot cycle, is lower temperature divided by higher minus lower temperature. So this is the COP max of a reversed Carnot cycle. So here we can see COP max is equal to COP ideal equal to COP reversed Carnot. All these three COPs are equal, and that will be equal to lower temperature divided by higher temperature minus lower temperature when we see these temperatures on TS plane. We can also understand these things by the help of second law of thermodynamics. If we want to understand heat engine, if we want to understand heat pump and refrigerator, then by the help of second law of thermodynamics we can understand it well. Here we can see the statements of second law of thermodynamics. First statement, that is Kelvin Planck statement, it was basically for heat engine. So what Kelvin Planck stated, it is impossible to develop a device operating on a cycle which produces work continuously by exchanging heat with a single reservoir. This device is also known as PMM2, that is perpetual motion machine of second kind, and it is not possible. So from this statement we have got the concept of heat engine, and we all know heat engine is a device which converts a part of heat into work and rejects remaining to the sink or surrounding. So heat engine is a cyclically operated device. So here we can see this is our heat engine, right? So from source we are getting Q1 heat, and from heat engine we are rejecting Q2 heat to the sink, and by the help of this heat transfer we are getting W net. W net is our net work. So if we want to find out the efficiency of this heat engine, then efficiency will be net work divided by heat supplied. So W net divided by Q1 will be the efficiency. In this figure, if you will see, this is the figure of PMM2, which is not possible. Why it is not possible? Because there is only one reservoir, that is source. There is no sink. So what Kelvin Planck told us, that it is not possible to develop a device operating on a cycle which produces work continuously by exchanging heat with a single reservoir. Kelvin told us that if you want to exchange heat, then at least there should be two reservoirs. So here we can see there is only one reservoir of source, there is no sink reservoir. So Q2 will be 0. That means whatever the heat we are supplying, that heat is completely converted into work, and that is not possible. So that's why the name given PMM2, perpetual motion machine of second kind, and it is not possible. Second statement is very useful for our subject point of view, because this statement tells us about a refrigerator and heat pump. So Clausius statement is, it is impossible to construct a device operating in a cycle which transfers heat from lower temperature body to higher temperature body without any external input. Means if we are having this refrigerator, and if we want to send the heat from lower temperature body to higher temperature body, then we have to use that work input. We have to take input from somewhere, otherwise this is not possible. This was the statement given by Clausius. So from there we have got the concept of refrigerator. So a refrigerator is a device which operating in a cycle maintains a body at a temperature lower than the temperature of the surrounding. So here we can see, we have already seen in earlier slides that COP of refrigerator is desired effect divided by work input. So what is the desired effect here? Desired effect is here Q2. We want to extract heat from storage, and we want to lower down the temperature of storage. So desired effect is this Q2, and work input is the difference of heat Q1 and Q2. So here COP is desired effect divided by work input, that is equal to Q2 by WIP, and here we can see COP of refrigerator is equal to Q2 by Q1 minus Q2. This equation is valid for reversible and irreversible refrigerator. Now if we want to find out the COP of refrigerator in terms of temperature, then we can see here, for a reversible refrigerator, using this formula Q1 by Q2, thermodynamic temperature scale formula, Q1 by Q2 equal to T1 by T2. We have studied these formulas in thermodynamics. So COP of reversible refrigerator is equal to T lower divided by T higher minus T lower. Here T lower is our temperature T2, T higher is our temperature T1. So COP of reversible refrigerator is T2 divided by T1 minus T2, or we can say COP of refrigerator is TL divided by TH minus TL. Similarly, for a reversible heat pump, for heat pump desired effect is this TH. For heat pump, this desired effect is this particular portion. We can see here. For refrigerator, desired effect is Q2, and for heat pump, desired effect is this Q1, because in heat pump we want to increase the temperature, in refrigerator we want to decrease the temperature, right? So refrigeration effect in refrigerator Q2, and for the point of view of heat pump we have to consider Q1 heat. So here we can see COP of reversible heat pump is T higher divided by T higher minus T lower, that is T1 divided by T1 minus T2. Now students, this is the most important topic of this lecture, significance of COP. What is the significance of coefficient of performance? Coefficient of performance is also known as energy performance ratio. So the significance of coefficient of performance is, for a given refrigeration load, smaller work input represents lesser electrical energy consumption and hence lower running cost. This means higher COP, and higher COP is always desirable, right? So mass flow rate of refrigerant is equal to m dot is equal to m by T, and COP of refrigerator, as we have already discussed, desired effect or refrigeration effect divided by work input. If we multiply mass flow rate in numerator and denominator, then we will get COP of refrigerator is equal to refrigeration capacity divided by power input. So this refrigeration capacity unit will be in kilowatt, and this power input will also be in kilowatt. So the final coefficient of performance of refrigerator is refrigeration capacity divided by power input. So that's all for today's class, students. In the next lecture, I will discuss numericals based on coefficient of performance. Thank you.